Okay, now we consider the projective gradient method for solving a linear constraint problem. So we have this minimization problem where the objective function is given by f, and the constraint is quite special. It's a linear constraint, and it's an equality constraint. It's also linear. Okay, we just need the x to be to satisfy this. Okay, so recall that the projective gradient method for in the general form should be given by this. So we have, suppose we already have the xk, then we take a gradient descent like that, just as we did at the beginning of this method, and then we apply this projection operator just to map this one back to the set of points which satisfy this. Okay, because we want our x to satisfy this. So in case that when we do the gradient descent, this is the outside of this set, or it doesn't satisfy this equation, then we try to project it back to the point where this condition is satisfied. And the projection pi here is the projection onto this set omega, which is described by the set of points which satisfy this ax equals to b. Okay, so that's pretty straightforward, just like what we have been talking about for the projective gradient method. But the problem right now is that how we actually compute this, because this is a very special set. So there should be a way to compute this easily, and this is the purpose in the following slides. Okay, so to do this, we first need to figure out what is this projection. So how do we compute this projection? This is pretty straightforward. Just everything that we need here have been discussed before, right, for gradient descent method. The only question right now is how to perform this projection. So now let's recall. We first consider a slightly simpler case. Suppose the set is given by the hyperplane rather than the omega, such that all the x satisfies ax equals to b. We consider a special case where this b is just 0. Where this b is just 0, in this case, the omega becomes a hyperplane, meaning that it is just the set of points such that ax equals to b. The set of points x such that ax equals to 0. And this is the hyperplane because of this, right? This actually gives us a linear subspace of the Rn, and this linear subspace is actually the null space of the matrix A. Right? It's all the vectors such that all the vector x such that x equals to 0. So it's just the null space of the matrix A. So it's the null space. Now we just need to consider, right now we just need to consider what is the projection of any vector onto this hyperplane or this subspace. So what it looks like is, suppose we have our n equals to 2, so it's R2 space. So x1, x2, then ax equals 0. In this case, will be just some subspace passing the origin. So this will be our ax equals 0. Or more specifically, this just means that a1 x1 plus a2 x2 equals 0. And you know that this is just a line passing through the origin. And the question right now is that if we have some point, say here, how do we project it back to this line? Okay, and this is in R2. But if it's a high dimensional space, n greater than 2, the thing is similar. It's a projection onto this hyperplane or projection onto this subspace. Okay, so let's consider how to do that. Suppose we have a vector v, it's like this point right here, and I'll consider how do we project that back into the hyperplane. And the projection is itself as an optimization problem, because we want to find the point on the plane or on the subspace that is closest to this point v. Okay, so we're trying to figure out, suppose this is the v vector, and we want to figure out the point x here, such that is closest point to v on this plane. Okay, and that's why the minimization problem is formulated in this way. So we'll try to minimize the distance between x, the point that we're trying to find, and the given point v, trying to find the point that is closest to the point v under the constraint that ax equals 0, meaning that under the constraint x is on this plane, right? So that's actually a minimization problem that we need to solve to figure out what the projection is. Okay, and actually we show soon later that this projection is actually a linear operation. So it means that it's a linear in v. So given a v, we just denote the projected point x here to be p of v. Okay, so for any vector v, you just apply the p to v, you get to a point that is the projection of v onto the plane. If v is here, then your projection here, this will be your p of v, which is p of v. And what just talking about is that the p essentially will be eventually will be just a matrix, and we'll see that soon later. Okay, and let's just give this notation p, meaning that it's a projection operator or projector of v to the point, to the point closest to the point on the hyperplane closest to v. Okay, since that we have this optimization problem to solve right now, just for projection, for this projection step, we need to solve this. And I know this is a linear constraint optimization problem, and it has pretty simple objective function, which is quadratic, and it has a simple constraint, which is linear. So we can first construct the Lagrange function, and then use the Lagrange theory or the Lagrange condition to solve it. Okay, to solve for the first order necessary condition for a minimal point. And in this case, the Lagrange function is written as that plus lambda times this. So this is because that if we have, generally we have, this is something that we have been extensively discussed before in the previous chapter. So suppose we're trying to solve a constraint optimization problem. We try to minimize fx subject to hx equals to 0. Then the Lagrange function is defined to be the f of x plus lambda transpose hx. Okay? Hx could be a vector valued function. And the lambda is a vector that has the same dimension as h. But this is a scalar right here, and this is the m-dimensional vector, m-dimensional vector, so in total it's just a scalar valued function. And in this case that we have here, the hx is just a times x, right? And fx is the quadratic function that we have here. So this is actually the f of x, and this is the h of x. Okay, so this is let's just focus on this problem right here. Temporarily ignore what the original function, original problem is. So this will be our objective function right now, which is the f, and then this will be the h. And now we have this, then we can derive the or write down the Lagrange condition. We know that this one can be easily obtained by taking the gradient of this L with respect to x and lambda. Right, that's the trick we learned in the last chapter. So when we take the gradient with respect to x, this becomes x minus v, and this becomes a transpose lambda, right? Because we know that we have been doing this for many times now. This is just a transpose lambda together, transpose times x. So when we take the gradient with respect to x, we just have the a transpose lambda left, right? That's the first condition. And the second condition is that take the gradient with respect to lambda, and then when we get this ax, so ax equals 0. But this one, we know the second one here is just the original constraint, which is ax equals to 0. Okay, now we have this, then we can try to solve for x and the lambda, and see this this gives us a first order necessary condition, and any minimizer should satisfy this. But actually, you can see that this system only admits one solution, and that solution is actually the minimizer. Okay, and this you can actually see this from the projection problem here. We have a strongly convex problem. We have strongly convex objective function. We take the gradient. We take the Hessian of this. It becomes identity matrix, which is always positive definite. And we know that in this case, the problem has a unique solution. Okay, if you can find point x that satisfies the constraint, then it will be only a unique solution, since the objective function is strongly convex. Right, and that's actually the case here as well. Okay, so now we have this, and try to solve this. And let's see how do we do that. We can see that ax equals to 0. So let's try to multiply this first equation by a on the left. Then we can get rid of this x. Okay, so let's try that. So when we apply a to the both sides of this first equation, we have a times x minus b plus a transpose lambda, then that's equal to 0, because originally it was equal to 0. So when you multiply the matrix A, it will be still 0. Right? And then because this ax will become 0, so what we end up with is just negative ab plus a transpose lambda equals 0. Okay, and now we can move the ab to the right. We have the a transpose lambda equals to ab. And now we will be able to get the lambda if we can take the inverse of this a transpose. Right? If we are able to take the inverse, then we can get what the lambda is. The question is, can we do the inverse? Can we take the inverse if this matrix is invertible or not? If this one is invertible or not? Well, let's think. Say A has the A is n by n matrix, so A should look like this, right? M rows, n columns, so it's pretty short and fat matrix. And we assume that the matrix A is has a full row rank, so that means the A has the rank of A is equal to the number of rows. Okay, because I have m rows and n columns, so the A has a full row rank. And in this case, we know that a transpose, which is m by m matrix, is like this times this, and this gives us a m by m matrix, and this matrix is guaranteed to be full rank. We have explained this before. When you have a full rank matrix A here, then a transpose will give us a m by m full rank matrix. Okay, so full rank meaning it's equivalent to saying that it is invertible. So that means lambda equals to a transpose inverse times AB. And then we solved for lambda. Okay, we know what the lambda is, and then we just need to plug this back into the first equation. We know lambda, we just put it back in here, and then we can solve for x. Right? Because x, remember that v is given, a is also given. So we can solve for this lambda x immediately after this lambda is solved. Right? Okay, so that's summarize that. We get this lambda equal to that, and then once we put this back into here, and then we move this v and a transpose lambda to the right, we'll get that. Okay, so x equals to this. So now we have actually solved for lambda and x. And you know that this x is what we need. It's the minimizer of this problem. Okay, and you can see that for any given v, my x is nothing but this matrix times v. And this is actually the P matrix we mentioned in the previous slide. It's a projection operator, or it's a projector. Okay, given any vector v, this P times v will give us the projection of v onto the plane. Okay, so that's the projector. Okay, So that's pretty clear, right? So as long as you know you know the matrix A, you can compute this matrix, and then, well, given any vector v, you just multiply this vector v by this matrix, then you get the projection of v. Okay, and it's very easy to verify that this matrix P right here, has a few properties. The first property is that it's symmetric. Okay, it's pretty easy to see that. Suppose we write this P. The P is this. Okay, and this is a symmetric matrix. It's pretty easy to see. Just take the transpose on both sides, and then you get back to the original matrix right here. Okay, it's pretty symmetric. Okay, you can try that by yourself. The second property is that the P satisfies this. The P squared equals to P itself. Okay, if you apply P twice, you get back to P. It's still P. And that's pretty easy to understand intuitively, because Px gives you P times V gives you the projection of V onto the plane. And that means that PV is already on the plane, plus I, which is a set of points x satisfying Ax equals 0. Well, if it's already on the plane, then you apply the P one more time, it will stay there, right? Because it's already on the plane. So that's why this is just equal to the PV. Okay, for any vector V, this will be true. That means the P squared is just equal to P. Okay, and we can also see that from the definition of P right here, because when you apply P twice, you can just compute this matrix multiplied by the self. Okay, let's see that what happens. Well, we have the same matrix multiplied twice, and we should get 4 matrix, because there are two terms right here and 2 terms right here. So when we break the square, I'll break the parentheses, we have 4 terms. The first term will be just I times I. The second term, this times this gives us I, while this times I or this I times this give us the same matrix. So we just need one of them, and that just multiply by 2. So it's 2 times the product of I at that matrix, and that will be just a original matrix, which is this. And then we have the last term, which is a product of this matrix with itself. Okay, and the 2 negatives becomes positive. So let's just see what happens. So it will be this matrix times this matrix itself. The A transpose inverse times A. Well, interesting happens here, because we have this A transpose right now. So we have a same thing, but the inverse here or here, doesn't matter. You can cancel Y with any one of them because they're the same. So suppose we cancel this. So this will be gone, okay? Because the inverse and the matrix itself is cancelled. And now you can see that what happens left. This is the same term as in this middle term, but it's just a single one instead of -2. This one has just +1 in front. So they cancelled. We cancelled one of them. And then we have just a y, I minus one of those. It's just A transpose inverse times A. And this is just the P itself. Okay, and that verifies the second equation. Okay, so the last one is that the projection of vector V is equal to 0 if and only if there exists a lambda such that there exists lambda, m-dimensional vector lambda, such that V equals to A transpose lambda. Okay, and what that means is if you project some vector V, you get 0. That just means that the A, so in this case, that means the V is in the null space of P. And if this is true, if and only if there exists lambda such that V equals to A transpose lambda, and here this means that V is in the range of A transpose. Okay, it's in the range of A transpose, meaning that it is in the, so A is like that, right? So the A transpose is like that. If your V can be written as A transpose times some lambda vector here, that means V is in the column space of A transpose, or V is in the row space of A's. Okay, or it is in the column space of A transpose, or in the row space of A. But in either case, we know that it's in somewhere here. So this statement just means that V is in the null space of P, even only if it is in here. Okay, so what that means by projection V, you get 0. It just means that the V is along this line. Okay, because in this case, when you project the V to the plane, you just get to 0, 100. And this line is actually the row space of A transpose. Okay, it's in the row space of A transpose. Okay, so the key is that right now, how do we show this? We show this because this is a sufficient necessary condition. We need to show both directions. Suppose this is true, let's show that this is true. And then we try to show the converse. Okay, suppose PV is equal to 0. If PV equals 0, that means this is P right here. PV equals 0 means that V equals to, we multiply this to V, you get 0. But you can see there are two terms right here, I and this, so you can move this second term to the right, you just have V equals to this times V. So this is the matrix right here. Okay, and that's this. That's what the V needs to satisfy. That's PV equals to 0. Well, if this is the case, then we can treat this part as lambda. Okay, we just define our lambda to be this part. And then you can see V equals A transpose times lambda. And that means this, right? So we found this lambda such that V equals to A transpose lambda, right? Pretty simple. Well, the other direction, suppose we know this is true. We know that there exists some lambda such that V equals to A transpose lambda. Let's check if PV equals 0. Okay, and suppose that V is equal to A transpose lambda, then we apply P to V. That means that we multiply this matrix P to the vector V here, and you can see that the first I goes with this A transpose lambda, so I keep it here. And then we have this term multiplied to the A transpose lambda, and you can see that they have this term, which will cancel with this term since they are inverse to each other. So I can just move this, remove this, then it will be A transpose lambda left. We have A transpose lambda here. So these two, it will be the same as the first term we got. So the difference will be 0, and that means that PV is equal to 0. And that is this. So we get back. If we know this, we'll also get back to this. Okay, so this is our sufficient necessary condition for each other. All right, so that's the third property of the projection matrix. All right, now we can derive a more general case. So previously we considered projection to the hyperplane or the subspace, AX equals 0. And now we suppose we have the B here. Let's see what's the projection there. You can show this by yourself. It's exactly the same steps as before, except that the 0 becomes B. So what you need to do is to write down the Lagrange function, and then find the Lagrange condition or the KKT condition, and solve for x and the Lagrange multiplied lambda. And then once you solve for them, you can see that what x is. And it turns out that x is pretty simple. The x is just the p times x, p times v as we did before, but minus this term. Okay, so if it's just a 0, then we will just have the PV here. But if there's a B here, then we need to subtract the additional term like this. And this will be our projection to this to this hyperplane, which is this. So remember that originally we're projecting to this hyperplane, but now suppose that B is non-zero, so it will be a shifted hyperplane. And when we project a point to this new plane, that is the result. So you projected, you first projected as you do for the subspace case when B equals 0, then just subtract this term, which is independent of V. Okay, it doesn't matter what the V is. Okay, leave this for as an exercise, and probably can figure it out within 1 or 2 minutes. Okay, it's a good exercise. Right now, we know that the projection of any vector v onto the hyperplane omega, described by the set of points x satisfying the x equal to b, will be just this. Okay, given vector v, you just compute that. Okay. Now we're ready to show what the projective gradient method is. Remember that we're trying to minimize the f of x subject to the x equals to b, and we know the projective gradient method is to compute for any point xk that we have right now. We compute the next point or next iterate by projecting the xk minus alpha alpha k, alpha is the step size, gradient f of xk. Okay, and then we can compute this first, which is just like the gradient descent method. Then we project this. But projecting this is simple as we did before. This is some vector v, and when we project this v back to omega, we just need to multiply this v by p and subtract. So it's just equal to p times xk minus alpha k, gradient f of xk, minus this matrix, which is A transpose inverse times B, right? That's what we did here. This term. You just need to subtract that. Okay, so that's essentially what the gradient descent, what the projected gradient method is for this case. Okay. Well, in this case, let's say there's a typo here. So a proposition that we can derive is that suppose we do this projected gradient method, then we want to reach to a point that is a minimizer of this problem. Okay, and the proposition says that a point x star satisfies a point x star that satisfies the first order necessary condition or the Lagrange condition for this problem if and only if the p times the projection of vector p times the gradient f at this point x star is non-zero. Okay, or in other words, if x star is a feasible point, meaning that ax star equals to b, okay, I should say that ax star equals to b, then the point x star is the Lagrange point, or it satisfies the Lagrange condition if and only if the p times gradient f x star is non-zero. All right. Sorry, I should say it is equal to 0, so I shouldn't have this right here. It's still just that. Okay, so it's a point satisfy the Lagrange condition if and only if this p times or the projection of the gradient f at x star to the plane omega is equal to 0. Okay. All right, so let's see why that's true. So we want to show that this is a sufficient necessary condition for this is that x star satisfies the Lagrange condition. So if this is equal to 0, so this is equal to 0 meaning that this is in the null space of P. Right? So it's in the null space of P. and it's in the null space of P if and only if it is inside the row space, the range of A transpose. It's in the range of A transpose. Well, that means this is because the third property that we have here, right, is in the range of A transpose. So it's in the range of A transpose means that we can find some vector lambda such that A transpose lambda equals to this, right? Because it's in the range of that. So you can form this vector here by making a linear combination of the columns in this A transpose, meaning that you can find some vector lambda star such that when you multiply this to lambda star, you get back to this. Well, let's take a negative lambda star instead of lambda star, then we get that. Okay, right? So this means that this is in the range of A transpose, or is in it can be formed by the linear combination of the columns in A transpose, and the combination coefficients will be given by some negative lambda star, and then we have this. Well, if this is true, this is the first one of the KKT condition, right, or Lagrange condition. Because when we have this problem, the first Lagrange condition will be the Lagrange function is this plus lambda times ax minus b. This is the Lagrange function, and take the gradient with respect to x, we get this. One. Okay, and that's for the first one, and then we have the second Lagrange condition because the x star satisfies the ax equals to b. So we have both of the conditions, and that means x star is a Lagrange point. Okay, will be a candidate for minimizer. And the goal of doing this projective gradient descent is to find such a point x star. Okay. So as we mentioned earlier, we can actually write down what the projective gradient method is by doing by following the form of the projective gradient descent. So remember that xk plus 1 equals to the projection here. This is what we wrote here, right? This is what you should do here. So you do that, and then of course because of the we know what the pi is, just the p times this minus this vector. So the p times this minus this vector will be our projection of the point onto the plane onto the hyperplane omega. And then recall that this P is just a matrix, so I can apply this P to this and this separately. So the first one gives us just the pxk. The second one will give us, or the one with multiply P inside here will give us this term. Okay, I can move this alpha k outside, it's just a constant. And then we can combine the first term and this last term I just got from the previous line. It's here. So we'll combine these two in the following because of the P was defined to be the projection onto the omega is just pxk minus that. So this is just essentially the projection of xk, right? So this whole thing here is just the projection of xk onto the omega, and this last term is kept right here. Okay, and then let's see, because we're assuming that we start from x0, that is already on the plane, and then we do this progressively. And then when we add xk, we know that it's still on the plane because we project some point back into the omega, and then we got xk. So the xk is supposed to be on the omega already. So when you project that onto omega, it will be just itself, since it's already on the omega. Okay, so we have that term, and then also have this last term. So essentially what the projected gradient method for this case is the xk plus 1 is nothing but xk minus this. And this is it's almost exactly the same as the gradient descent method, except that we have additional P matrix here in front of gradient f. Okay, so that's the only difference from the standard gradient method for this case. And as we said before, we are always on the plane because when you do this projection, we know that we'll be always on omega. So and this is how to guarantee that we're on omega. We just need to have the previous point on omega, and then we separate this term, which is makes us still on omega, right? No. Well, for this case, we have been very clear about what the projective gradient is doing, and the only thing that we need to handle in practice is to determine this step size of k. Okay, so that's the only thing that we need to figure out in practice. Then we can get this algorithm running. Right. So, for example, one way, a simplest way to do this is to use the steady descent method, which finds this alpha k by minimizing this line search function, right? Because we need to determine what this alpha is. So let's just say that everything else is fixed, and then go along this line. How large this alpha needs to be so that this f is minimized along that line. Okay, so like that we have xk here, and then we decide that this is negative gradient fxk, and we have the projection in front of that to make sure that we go this direction, we stay on the omega, and the only question becomes how far we should go. And this alpha, we start from alpha equals to 0, then we gradually increase alpha, then we're basically going along this line, and we'll track the function value along this line. And when we find the minimum value, we'll stop there, and that is our step size, alpha. Okay, that's how we decide the alpha k. That's a conceptually that's the reasonable way of doing that, but we know that in practice we rarely do this accurately because this one itself can be expensive. But this is some in principle it should be working. Okay. So now let's summarize a property of the projective gradient descent method. It says that if we generate this xk by the projected steady descent method, as we did here, we search for alpha k to be the minimizer of the line search function. Then, as long as, so this is where the error is, this should be not equal to. Okay, as long as the p gradient f at xk is still non-zero, then we can further decrease the function value. That means the next point will definitely have smaller function value than our current point xk. Okay, and I'll show that why this is true. Okay, so suppose we have reached to a point xk where the p gradient f at xk is still non-zero. Then let's see if we can further reduce the function value. Okay, suppose we have the xk, then we have everything we need for the projective gradient method. So this will be our next point. The only thing that is not determined yet is the alpha. So let's say that this part, we plug this back into the f. This will be a function of alpha only, right? Just like what we did for line search function. Okay, and once we determine the alpha, this will actually give us this box thing will be the next point xk plus 1, and we'll get the function f at that point. All right, so now suppose we define this line search function of alpha, then we know that by taking the gradient with respect to alpha, so the phi prime at alpha, you know that this is a univariate function that is scalar valued as well, meaning that it takes the scalar alpha and we get the scalar value of phi of alpha. So when we take the derivative, we just take the derivative with respect to alpha, and then you can see take the derivative of this with respect to alpha. We should apply the chain rule, right? We first apply the gradient of the outside function f, so that gives us that, and then we take the gradient of the inside. So the inside here is a function of alpha, but it's a linear function of alpha. So when we take the gradient of this with respect to alpha, we will get negative of p times this, because this is the thing multiplied to alpha. Okay, so we have this and also the negative right here. Okay. Now, so remember that this is a row vector. This is a column vector, and take the transpose, it becomes a row vector. This P is a square matrix. This transpose, this one here is again a column vector because it's a gradient f at some point. So this is a n-dimensional vector right here. This one, if you include the transpose, it becomes the 1 by n. And this P right here is n by n. And right, this one here is n by 1. We have been doing this for many times now. So, you know, just giving us the scalar phi prime. Okay. All right, so the purpose of doing that is you can think this way, just like we did before. Well, we have, this is our 0. This is the phi of 0. And this no is just the f of xk. Okay, because when you plug in x equals to 0, alpha equals to 0, then you just get back to f of xk. Because when alpha is equal to 0, this term is just gone. So you have f of xk. And then you check that when you increase alpha, can you get a lower value than phi of 0? And this is tracking the function value along the line, along this line, when alpha gradually increases. So when you gradually increase, then you check the function value right here. And if you know the derivative of phi is negative at 0, meaning that it's negative, it's going down, then you know it must be something like this, right? If the negative, if gradient of phi or derivative of phi at 0 is negative, then it must be going down. And we don't know how far it goes, but it must be going down initially. Eventually it may go up somewhere, but at least near 0 it should be going down. Okay, and this is what we're trying to show. If we can show that, then we know that there will be at some point somewhere that has a function value smaller than the phi of 0. Okay, so we just need to check if the phi prime at 0 is negative. Well, to check phi prime, we just need to verify at phi prime at alpha is generally given by the right hand side. So phi prime at 0, we just need to plug in 0. When we plug in alpha equals to 0, this is the only place that has alpha on the right hand side. So when we plug in alpha equals to 0, this is just gone. So we will just have a negative gradient f at xk. Then we have the transpose, we have the p, we have this another gradient right here. Right? So you can see that this is the same term as this. And remember that the p is equal to p squared. That's a property of p we showed before. So we have the p equals to p squared, and it's also equal to p transpose p, because the p is symmetric. So essentially we just have the one p goes with this, another p transpose goes with this. So we just have the p times this squared. Okay, so this is nothing but just this negative gradient f at xk. Transpose, we have the p transpose of the p, we have another gradient f at xk. Okay, and then we know that by combining these two, we have the p gradient f at xk, this together transposed. So same vector transposed. So same vector transposed, and we know that this is inner product of the vector with itself, and it's just negative of the square norm of that vector. And that must be less than 0 because we'll assume that this is non-zero vector. So if it's non-zero vector, this norm must be negative, strictly positive. And then with the negative sign here, it becomes strictly negative. So that means it's negative 0. It's less than 0. So meaning that this is really going down right here. And you know that there will be some point which we call, say, alpha k. And that's the minimum point you can get. And eventually you'll go up. And maybe you'll go down somewhere, but let's say that's the minimum point. Or maybe it's going down, up and going down again. But anyway, the alpha k will be the minimum point along the line. So because this is the criterion we use to determine this. But actually, as long as this phi prime is true, then there are many ways to choose the alpha k. It doesn't have to be the minimum point, because you know that once it's going down, there will be a range of points that have negative value or have smaller values than phi of 0. Okay, and you can choose any alpha in that range, and that will give you a reduced function value. Okay, you can just choose the alpha, and then the function value will decrease. And then by alpha k, we plug in alpha k, and this inside here is the new point xk plus 1. And that shows that we can further decrease the function value. Okay. One more remark that I want to make here is that when the function f is convex, then actually this will be sufficient to say that the global minimizer is reached. Okay, so it's not just a necessary condition, as we said earlier. This equals 0 for some feasible x star means that x star is a Lagrange point, meaning that it satisfies the first order necessary condition. But if f is convex, then this is actually also sufficient. Okay, it's sufficient to say that x star is a global minimizer of f. Okay, and this is actually due to the property of convex functions we introduced in the last chapter. When the function f is convex, we can often convert, or we can often guarantee that the necessary conditions are also sufficient. Okay, and back to this situation, we can easily see that as well. Because f is convex, so the f is convex, then theorem says that if f is convex, then this condition, they also say that x star is feasible. And x star is feasible. Feasible means that ax star equals 0, equals to b. Okay, if this is true, then this condition is also sufficient, meaning that it's equal to 0 if and only if x star is a global minimizer. And how do we show that? Just because that is this, this equal to 0 is a necessary condition, but under the condition that f is convex, this necessary condition becomes sufficient as well. Okay, so this equals 0, meaning that x star satisfies this necessary condition, which is the Lagrange condition, and because f is convex, the necessary condition becomes a sufficient condition. So x star must be global minimizer. All right. Okay, so that's the special case we for projective gradient method. When we have, in general, we can apply as we did before. In general, we have a function to minimize, function f to minimize over the set arm omega. If we know how to do the projection back to omega easily, then we can just do the projective gradient method, which is similar to the gradient descent method, except that after we do the gradient descent step, we project the point we got back to the set omega. Okay, and what we discussed just now is a special case where the omega is a hyperplane. It's specified but by the points x, where ax equals to b. Okay, it's a hyperplane. But in general, that's not necessarily the case, right? We can have very complicated constraint. And in that case, how do we cannot really, we don't really have a space or a subset omega to project to. Instead, we're given a equality constraint or inequality constraint or both to describe the constraint set. In that case, we will not be able to find the projection operator. And the question right now is how do we handle those cases in general? Okay, so this is called a Lagrange algorithm. It is used to solve minimization problems with equality and inequality constraints. So let's first consider the situation with the equality constraints. The question right now is given by, the problem we're trying to solve right now is this equality constraint minimization problem. We are trying to minimize f of x under the constraint that hx must be equal to 0. Okay, so this is the equality constraint problem we mentioned before. Now let's assume that f and h are both twice continuously differentiable, meaning that they are second order derivative for f, or the second order Hessian for f, and also second order derivative for h. They're all continuous. Okay, second order derivatives are continuous. right? So in this case, let's see how do we solve this in practice. So remember that the goal right now is to find a Lagrange point, but this is actually giving us a necessary condition for a minimizer. It's just like that when we try to solve, we're trying to minimize fx, right? Or what we can do is to do the gradient f equals 0, find the points satisfy this. Right? This will give us all the critical points, and our minimizers will be among them. Right? That's what actually the gradient descent method is doing. Just trying to give us a point by iterating this. For k gradient f xk, and hopefully when the xk goes to when the xk converges, then both sides will have this limit point equal, and they will be cancelled. We'll have the gradient f equals 0, and that's supposed to give us the a critical point. And we're doing the similar thing here. So suppose we're trying to find a critical point for this problem, and that critical point is actually a Lagrange point. Okay? So to do that, first write down the Lagrange function. So fx right here, hx right here, so hx times lambda will be our Lagrange function. And the Hessian of this Lagrange function with respect to x only. Okay, so we treat lambda as a constant. We do that with respect to x only. We have the Hessian of that, and also the Hessian. This H has m components, and each one will apply a Hessian. Okay, we'll compute the Hessian. So that will be actually it will be a 3-dimensional matrix, because when you do the Jacobian, that will be m by n. But when you apply the Hessian, that will be m by n by n. When you do the transpose, this is like, so this is pretty interesting. You can it's pretty hard to imagine, but that's actually the case. When we do the h to apply the Hessian to this, we'll get this. So this matrix is actually 3-dimensional. It's actually, after the transpose, it actually becomes n times m. Okay, it's like a cube. Okay, and the reason is that you can think that you have m components of H, and each of these components, when you take the Hessian, gives you a m by n matrix. So you have m of them stacked together. That's your that's this term. Okay, that's this term. And then you multiply lambda, which is m by 1. Then you can cancel with one of them m. Then there will be it will give you an n by n matrix. So it's like that. The dx square H is like that. So this is n, this is n, and this is m. Okay, and you have another m-dimensional vector, which is, say, I will say this in this way. So this is your lambda, which is m-dimensional vector. And then your lambda will be multiplying to each of these n square vectors, taking inner product with each of those, and then when you multiply them together, you'll be getting an n by n matrix. Okay, so that's the Hessian. Okay, so let's keep those as a notation, and now let's derive what the so-called Lagrange algorithm for solving this equality constraint problem. Okay, so with that problem, the Lagrange, this is actually based on the Lagrange condition. When we have the Lagrange function, we can get the Lagrange condition by taking the gradient of the Lagrange function with respect to x and the lambda. When we take the gradient with respect to x, we know that this just gives us this first equation that we have been talking about for many times. And then the second condition is just take the gradient of the Lagrange function with respect to the lambda, and that will be giving us this hx equals 0, which is just the original constraint for h or for x. All right, so now remember that the goal is to find a critical point for the constraint problem, which are the points that satisfy this condition. Okay, we're trying to find such x. Well, we can remember that when we are handling the n-constraint problem, we just do the gradient descent. Right now, the gradient descent is like what I just showed here. It's just like doing that. Okay, try to find this point, then we just do that. Well, the situation that is this goes right here. Since we don't know what x is, so we just do this iteratively. We have the xk, we put the xk, the current estimate here. Then we do the gradient descent from xk. We'll get xk plus 1. Then we do this iteratively, right? And now let's go back to this case. If we're trying to find a critical point, meaning that it satisfies this, we can do a somehow similar gradient descent. So we want this to be 0, right? We just put this right here and plug in xk, substitute x by xk, and then we iterated this like we were doing the gradient descent using that as your gradient, as our gradient. Okay, so just plug in this, plug in x equal to xk, and then we'll put it here, then we'll do the gradient descent on xk. Okay, so xk plus 1 equals xk minus some step size r per k times that. Right? That's for x. That's how we update x. But the lambda needs to be figured out as well. Well, then in this case, we'll also need a gradient for lambda. Well, for lambda, we're going to work on this one. We're going to update lambda k by doing this computation. We add this term to xk with the step size beta k. So this is like gradient ascent. So what do I mean by that is we actually are trying to do this thing. We're trying to minimize we're actually trying to min-max this. What do I mean by that? I will explain soon. Okay. All right. So what this means? We plug this back in. We plug in this lambda x lambda L of lambda, sorry, L of x lambda back in here. We know this f of x plus hx transpose lambda. Well, interestingly, let's focus on this part. So what this means is that for any fixed x, I'm going to take this maximum of this with respect to lambda, see whatever I get. That will be a function of x, because once we change x, we'll potentially change the value here. So this will be a function. As we're taking the maximum with respect to lambda, this becomes a function of f. Okay, this becomes a function of f right here. Let's see what that is. So if this is the function of f, say if hx equals 0, so if hx equals 0, then let's say that if the hx equals 0, at that such a point x, this is just 0. It doesn't matter what lambda is. You take the maximum, it doesn't help, because this whole term is just gone, right? So what this value is just f of x. So when hx equals 0, it's just f of x. Okay, nothing changed. Well, if hx is not 0, so if hx is not 0, well, in this case, doesn't matter what f of x is. Well, this is a non-zero vector, and I can choose this lambda, just make this lambda extremely large. Say I can choose the lambda to be the hx itself times some super large number, and in this case, we multiply this to lambda. Say I have this hx transpose lambda. Well, if I choose this lambda to be just hx itself times some super large number, I call it phase c. Then this becomes the c times the hx norm squared. And since hx is non-zero, I know this is positive. And then since I have the freedom to choose c, and just to make c going to infinity, I make it go to infinity, this will be just going to infinity. Okay? So I can make this arbitrarily large. It doesn't matter what fx is. I can always blow this up by choosing larger and larger lambda. So the maximum actually here is 0. Okay, so maximum that we have here, maximum I have here is infinity. So it's actually positive infinity. right? So this inside function is a function of x, and it takes it could be two cases. If hx equals 0, then this is just fx itself. If this hx is non-zero, then this is infinity. And what this says is that if hx satisfies the constraint, then we're okay. We're just minimizing this. Okay, so this is exactly what we're trying to do. We're trying to minimize the f under the constraint that this is equal to 0. So if it's equal to 0, then we're actually minimizing the fx, because this part will be just f of x when hx equals to 0, when the constraint is satisfied. When x is non-zero, when hx is not 0, meaning that the constraint is violated. In this case, you should not do anything, because this will be positive infinity. There's no way to minimize it, right? It's always positive infinity. And this is because x is infeasible, and we should not consider such kind of x. Okay, so that's actually what this min-max is doing. So when you do the maximum with respect to lambda, this actually tells you gives you a very interesting function. It already takes the constraint into consideration. Okay, so in this case, we know that when we do the minimization, we can only do the minimization to the first case when hx is actually equal to 0, and we're taking the minimum of f under such constraint. That is the original constraint problem that we have. Okay, so that's what I'm trying to say here is that the Lagrange function actually gives you a very interesting structure. We're actually doing this min-max. Well, if it is the case, let's say that if for every fixed lambda, you would like to minimize this function with respect to x, so you would like to do the gradient descent. And that is why for fixed lambda, you would like to do this. K plus 1 equals to xk minus alpha k gradient L of xk lambda k. Okay, so for fixed lambda k, you would like to do this. Take the gradient with respect to x, since you are trying to minimize the Lagrange function. But on the other hand, you would like to maximize this Lagrange function with respect to the lambda. So it will be lambda k plus 1 equals to lambda k minus, say we choose the step size beta k. And since we are trying to maximize this, we're going to do the gradient ascent. Instead of negative gradient, we do the positive gradient. So it's positive gradient lambda L xk lambda k. Okay, so it's like the xk is fixed, but we do a gradient ascent with respect to lambda. Okay, so you can see that that's actually just a gradient descent on x, but a gradient ascent on lambda, and then we'll get the update. Okay, that's what I said here. So it's like we're doing the gradient descent for x with the step size alpha k, and the gradient ascent for the lambda with the step size beta k. Okay, that's actually a way to memorize this Lagrange function. It's actually pretty motivated because we're actually doing the min-max for this L. So this is in generally called the saddle point problem, because we're not really minimizing something, but we're minimizing with respect to one variable, but maximize it with respect to another variable. So it's like a saddle that we're trying to find the saddle point of this function. Okay, and what do we do in practice to do the gradient descent for one and the gradient ascent for the other? Okay, so that's the motivation for the gradient descent method for the Lagrange algorithm. So in practice we will do we can choose alpha k, beta k differently, and in practice there are also different types of variations of Lagrange method. For example, if we already computed this xk right here, then xk plus 1 from here, then why not just use the xk plus 1? It will be even better than xk, since we're updating this lambda k plus 1 after xk plus 1 is computed. Let's just use that. Okay, since this is supposed to be or expected to be a better point than xk. So we can do that. So there are many variations, and we're not going to. Well, this is what is still active research area, and depending on the application or the problem, the people are designing efficient algorithms to solve them with high efficiency and accuracy. So this is actually a major topic in optimization research or operation research. Okay, and yeah, let's go back to this. And then if this is the one that we're trying to do now, then we want to figure out if this one is going to converge. Generally speaking, the convergence of this algorithm is pretty hard to get. It's pretty difficult to get because the problem right now is highly non-convex. We didn't give much constraint or restriction on f and h. They could be convex functions, could be non-convex functions. The only thing we require them to be right now is that they are all C2, but C2 function could be very complicated, could be highly non-convex. So it's hard to tell if this algorithm is going to converge. What we can tell is called so-called local convergence, meaning that if we started with some point x naught lambda naught close to a Lagrange point, then this algorithm is guaranteed to converge, provided that the step size were chosen sufficiently small. Okay, so you can see there are lots of if, there are under lots of conditions, but the one sentence distribution of the result we're going to get is that when we start from some point close to the local minimum, the Lagrange point, or the critical, it's like the critical point right now. If we start from somewhere close and then we choose the alpha beta small enough, then the algorithm that we describe here will converge to that point, to the KKT point, the Lagrange point. Okay, that's what we're going to show. But at least right now we can, think this as just a proof of concept. Give us some confidence. Suppose we can really get a convergence, meaning that xk converge to x star, convert x star lambda k convert lambda star. Now what happens is this goes to x star, this goes to x star, so they will be cancelled on the two sides, right? This will be going to lambda star. This also goes to lambda star, so they will be cancelled. Then we'll have x star here, lambda star here, lambda star here. So that means this part is equal to 0 when we plug in x star, lambda star. And that is exactly this condition right here. This Lagrange condition here. That means x star, lambda star would be a Lagrange point. Okay, and that should be okay. That should be anticipated, or that should be desirable, since we're trying to get convergence to a Lagrange point. Okay, and this seems to be true. Okay, and in particular, we do the analysis soon later. We're going to show that we're going to choose this alpha k beta k to be equal, because you can see that if you choose them differently, then you can simply just scale the lambda. You choose the lambda in a different way. That will be it's not a some generality we lose here. Okay, so this is we're going to discuss this convergence right now.